So, um, if you want to build the next generation of global wireless technology, you'd probably assume the work starts in, I don't know, some sterile air-conditioned laboratory in Silicon Valley, or maybe a pristine university campus.
Right, yeah, you think of white lab coats and clean room.
Exactly. But today, we are looking at a blueprint that suggests you actually start at the bottom of a dark, damp coal mine in Vietnam.
Which is just, I mean, it's a massive pivot from how we usually think about education and industry.
It really is. And for you listening right now, someone who wants to understand not just where technology is today, but how entire nations are positioning themselves to control the tech of tomorrow, this deep dive is going to be genuinely fascinating.
Yeah, we are pulling from a really detailed interview from Viet Times. It's an interview with Dr. David Nghiem. He's the founder of the Talented Minds Agency, or TMA for short.
And the mission here today is to unpack this really bold, highly specific national blueprint. We're looking at how a developing tech sector is attempting to take these purely theoretical students and forge them into what they're calling global tech eagles.
Yeah, tech eagles. It's a great term.
It is, and they're doing this in the brutally difficult, highly specialized arena of antenna and microwave technology. So, okay, let's unpack this because you really can't build a world-class industry without understanding the raw materials you're working with first.
Right, and in this case, the raw material is human potential. Dr. Ninh Mi refers to the current generation of young Vietnamese engineers as sparrows.
Pharaohs, okay.
Yeah, and he emphasizes that they have this incredible potential. Like their logical reasoning is just off the charts, they're highly intelligent, and they have this massive, genuine hunger to learn.
So the raw talent is clearly there. I mean, they've done the math, they've passed the heavy exam.
Oh, absolutely. The problem, though, is that they're entirely trapped in what he calls the academic ivory tower.
Ah, the classic trap.
Right. They've absorbed textbooks full of, heavy, complex theory, but they possess zero actual combat experience.
Combat experience. I love that phrasing so much because it implies that um, the real world fights back.
It absolutely does fight back.
Yeah.
When these brilliant students step into an actual industrial environment, they tend to freeze up.
Because the theory only takes you so far.
Exactly. They are suddenly dealing with extreme, uncompromising standards for, security, hardware performance, and physical safety. They realize very quickly that knowing the equation on a whiteboard just doesn't translate to making a device actually function in a chaotic physical space.
I think we need to pause here and look at why this specific field, antenna technology and microwaves, is so incredibly unforgiving. Because let's think about a software engineer.
Okay.
If you write a piece of code and you make a logic error, the program crashes. What do?
You just fix it.
Right, you hit backspace, you rewrite that line of code, you compile it, and you run it again. It's entirely virtual. The cost of failure is literally just a few seconds of your time.
Yeah, it's practically zero stakes for making a mistake. But dealing with invisible radio waves and electromagnetic fields, that is an entirely different beast.
It feels like trying to tune a really complex physical musical instrument while completely blindfolded. Like you can memorize all the sheet music in the world. You can sit down and do the calculus on the acoustics of a concert hall. But none of that theory actually matters until you pluck the string.
Yes.
You have to actually hear how that sound wave resonates, how it bounces off the walls, and how it hits the listener's ear in a physical, three-dimensional room.
That analogy gets right to the heart of the physics here. Paper calculations and, pristine computer simulations, they will only get you so far when you're dealing with electromagnetic fields.
Because reality is messy.
Exactly. The math is famously dense, but as Dr. Nghiem points out, those equations are functionally useless without rigorous physical lab testing. You have to physically manufacture the antenna structure and measure its behavior. The real world is incredibly messy.
Right, you have temperature swings, physical obstructions in the room, weird interference from like a microwave oven 2 rooms over.
Yeah, literally everything impacts the signal. And understanding this niche, antennas and radio frequency integrated circuits, or RFICs, it's a vital.
RFICs. Can you break that down real quick?
Sure. So an RFIC is essentially the physical microchip that takes an invisible analog radio wave that's just pulled from the air, and it translates it into the digital ones and zeros that a computer processor can actually understand.
Wow, okay.
It is the invisible backbone of the modern world.
So without that specific translation hardware, all of our gadgets are just useless.
Completely useless. We talk about the Internet of Things or IoT, this massive network of smart thermostats, industrial sensors, medical monitors that are constantly communicating without human input. We talk about mobile networks. All of that relies entirely on antennas and RFICs. Your smartphone, no matter how advanced or expensive the processor inside it is, it's just a very expensive piece of glass and plastic if it can't physically grab a signal out of the air.
And the source material highlights another massive blind spot for these sparrows. It's not just a lack of physical lab skills either. The ivory tower has, completely isolated them from the actual business of innovation,
Oh, yeah. They don't know how to navigate international patents at all.
which seems like a fatal flaw if you're trying to build a national tech hub.
It really is. If a young engineer doesn't know how to search the global database of human knowledge, they can't see what's already been invented.
Right, they're just guessing in the dark.
Exactly. So they end up reinventing the wheel instead of building upon existing technology. And furthermore, Dr. Nghiem points out the severe lack of understanding regarding intellectual property protection.
Meaning they could invent something genuinely brilliant in a university lab, and because they don't know the legal mechanisms to protect it, some larger competitor just swoops in and takes it.
Yep. They know the math, but they just don't know how to survive the business side of it.
Which leaves you with a workforce that looks amazing on a university grading sheet, but is functionally unprepared for the hyper-competitive realities of the global tech industry.
Precisely.
But, okay, I want to push back on this entire premise for a second, though. Here's where it gets really interesting. I understand the problem, but let's look at the architect of this solution, Dr. Nghiem.
Okay.
The interview notes he was the Associate Dean of Cullen College and the Director of the Telecommunications Center at the University of Houston. That is, the very definition of an elite academic.
Sure, yeah.
Doesn't reaching that level of academia usually mean separating yourself from the gritty industrial work? It's a classic trope, right? The tenured professor sits in the nice air-conditioned office and sends the grad students down to the basement lab to get their hands dirty.
Right, the stereotypical academic.
Exactly. So how does a guy with that specific background actually change the mindset of these young theory-obsessed engineers?
It's a totally fair question, but his resume is actually a masterclass in bridging the gap between heavy industry and academia. Before he was a dean, he spent decades acquiring the exact combat experience he says these students are missing today.
Oh, really?
Yeah, he worked at the absolute highest levels of global hardware. He was at Qualcomm, building mobile chips. He worked at the Harris Corporation, dealing with secure defense communications where the hardware literally cannot fail under any circumstances.
Wow. Okay.
And he also spent time at Medtronic developing life-saving medical technology.
That's a serious track record.
Yeah.
And the patent list alone is kind of wild. I saw he holds 17 patents from the U.S. Patent and Trademark Office.
Yep.
We're talking high-performance mobile antennas, long-range explosive detection devices. He even has patents for RF sensors designed to detect skin cancer. Which, wait, let's pause on that.
Yeah, that specific patent is a perfect example of his whole philosophy.
But how does an antenna detect cancer? That sounds like science fiction.
Right. It's fascinating. It relies on the way electromagnetic waves interact with human tissue.
Yeah.
So cancer cells typically have a higher water content and a completely different density than healthy skin cells.
Okay.
So if you design a highly specialized RF sensor to emit a specific radio frequency into the skin, the waves will actually reflect back differently when they hit a tumor compared to when they hit healthy tissue.
Oh, wow.
Yeah, it's using the exact same fundamental physics that allows your phone to talk to a cell tower, but applying it to non-invasive biomedical diagnostics.
That is just incredible. So he's taking telecom physics and turning it into a literal medical device.
Exactly. And that leads directly into how he teaches. You asked how an elite academic gets students out of the ivory tower.
Yeah.
Well, the source text gives this amazing anecdote about Dr. Mengiem's philosophy, which he calls science for humanity.
I read this part, and it completely subverted my expectations of what an engineering mentorship actually looks like.
Yeah.
I mean, he isn't taking these students on tours of pristine corporate campuses in Silicon Valley.
No, not at all.
He is literally taking them deep underground into the coal mines of Quang Ninh province in Vietnam.
It is the ultimate antidote to the ivory tower. They go down into those mines to research and deploy highly specialized wireless communication equipment.
And let me guess, standard Wi-Fi or cellular signals just don't work through hundreds of feet of solid rock.
Oh, not even a little bit. The geological interference is massive, the environment is incredibly dangerous, and the hardware they're down there designing, it has one job, which is to keep miners connected so they survive in an emergency.
Right.
Dr. Nghiem physically takes his students down there to show them that their equations have to work in the mud, in the dark, under intense pressure to keep real human beings alive.
That honestly gives me chills. He is physically demonstrating what combat experience actually means. It forces the student to realize that, an engineering failure isn't just a bad grade. An engineering failure means a miner's radio doesn't work when there's a cave-in.
Exactly. He calls it transferring the fire. To be a true mentor, you can't just hand a student a syllabus and walk away. You have to get into the trenches with them and actually model the behavior of using hard science to solve the most dangerous problems society faces.
So the philosophy is clearly established, and it's super powerful.
Mm.
But how does TMA actually scale this? I mean, taking a handful of students to a coal mine is great, but we are talking about transforming an entire nation's workforce here.
Right, the logistics of it.
Yeah, what is the literal actionable blueprint to make this happen on a massive scale?
Well, the first phase is restructuring local university education. So TMA is partnering with universities across the entire country, from Hanoi and Nghiem up in the north, all the way down to Ho Chi Minh City, Can Tho, and Trevin.
Okay, so it's a nationwide effort.
Yeah, and they're implementing these short-term, highly intensive, hands-on lab courses.
And the curriculum focuses on what he calls the design, measure, optimize cycle.
Yes, and the key word in that cycle is measure. In a standard academic setting, a student might design a circuit, simulate it on a computer, and just turn it in for a grade.
Right, all virtual.
But in these labs, they have to physically build it and measure the real-world output. When the temperature in the room changes and the antenna suddenly detunes, they have to figure out why and optimize the physical design right there.
So they're forced to become proficient technicians before they're even allowed to call themselves engineers.
Exactly. That handles the domestic side, getting the students comfortable with, like, a soldering iron and a testing rig. But the source material highlights a much larger international ambition here. The real crown jewel of this whole strategy is the Sponsor a Student program.
Oh, this part is fascinating.
This is where Dr. Nghiem leverages his entire career network. TMA identifies the absolute brightest students from these domestic labs, the top sparrows.
The ones who survive the coal mines.
Yeah. And they then connect these students directly with elite U.S. university professors. We are talking about heavily funded research and development projects at places like Columbia, Rice, the University of Houston, and Texas A&M.
And these aren't just like standard study abroad programs where you sit in the back of a lecture hall and take notes for a semester. These students are being brought in as active, contributing researchers on real projects.
Right. And here's the crucial component. They receive 100% full-ride scholarships for their master's or PhD programs.
Wow.
Yeah, all financial barriers, which are, often insurmountable for families in developing nations, they're completely removed.
Okay, but this brings up a massive structural question.
Okay, what is it?
If you identify the absolute smartest, most capable young minds in your entire country, and you send them to Columbia or Rice for free to work on these cutting-edge, heavily funded global projects,
Yeah.
aren't you just engineering a massive brain drain? Once a student gets a taste of that level of R&D funding, the quality of those pristine labs and that standard of living, why on earth would they pack up and come back to Vietnam?
It is the ultimate risk for any developing nation. And you're right, many have lost generations of talent exactly that way. But Dr. Nghiem views this as a mandatory incubation period.
Mandatory.
Yeah, you simply cannot build a world-class technology sector if your engineers have never actually seen what world-class looks like in practice.
Ah, I see. You have to know the standard before you can replicate it.
Precisely. They have to develop a global mindset. They need to learn firsthand how top-tier labs manage patents, how they protect their intellectual property, and how they bridge that gap between academic research and viable commercial products. Dr. Nghem's stated expectation is that these U.S.-trained engineers will return as tech eagles.
Armed with that science for humanity fire he instilled in them early on in the coal mines.
Yes. They return not as junior employees who need hand-holding, but as the seasoned leaders who will actually build the domestic R&D infrastructure from the ground up.
But that requires an ecosystem for them to land in, right? If these highly trained tech eagles fly home to a country that doesn't have an industry ready to utilize their new skills,
Yeah.
all that education is just wasted.
Exactly.
Which brings up this massive, multi-billion-dollar debate happening right now about how a nation should actually spend its tech budget. So what does this all mean? We have to look at the macro vision here.
To understand the TMA roadmap, we first need to look at what Dr. Nghiem is urging Vietnam to aggressively avoid. He warns them heavily against the foundry trap.
The temptation to build massive microchip factories.
Right. In the current global semiconductor rush, the immediate political instinct for a lot of nations is to announce, hey, we're building a wafer fabrication plant, a foundry.
These are those sprawling facilities that actually print the microscopic circuits onto silicon wafers.
Exactly. And Dr. Nghiem says that jumping straight into that is a catastrophic mistake for them right now.
Why is that? I mean, foundries seem to be where all the money is.
Because building and maintaining a competitive, modern semiconductor foundry costs literally tens of billions of dollars. But more importantly than the money, it requires a hyper-specialized supply chain for rare chemicals, a flawless power grid that never blinks, and an army of experienced floor technicians that a developing tech sector just simply does not have yet.
I look at it like this. Committing $20 billion to build a foundry right now would be like trying to pour a massive, incredibly expensive concrete foundation for a skyscraper right in the middle of a swamp.
Oh, that's a great way to put it.
You just don't have the bedrock. You're going to sink all your capital into the mud,
Yeah.
and the building is never going up.
That captures the danger perfectly. You are trying to compete against entrenched giants in Taiwan and South Korea who have a 30-year head start on pouring that exact concrete.
So instead of trying to fight that unwinnable battle, Nghiem is suggesting they become the elite architects who design the skyscraper and the master interior finishers who make the building actually livable and valuable.
Right.
Like, let someone else manufacture the raw concrete. Let someone else print the raw silicon. Vietnam should control the design and the high-value finishing work.
And in the semiconductor industry, that finishing work is called OSAT. That stands for Outsourced Semiconductor Assembly and Test.
Now, when I first saw the term assembly and test in the source, my brain immediately went to software. Like, I assumed OSAT meant writing the drivers, coding the firmware, or running software diagnostics on the chip.
A lot of people think that, but it is actually a deeply physical, gritty process, which ties right back to why they need those hands-on lab skills we talked about earlier.
Okay, so what is it physically?
Well, when a raw silicon chip comes out of a foundry, it is basically a naked, incredibly fragile flake of glass.
Oh, really?
Yeah, it's entirely useless on its own. It doesn't have the physical metal pins required to plug it into a motherboard.
Oh, so OSAT is physically building the housing for the chip.
It's building the housing, but at a microscopic level. It involves using these automated machinery to weld gold or copper wires, and we're talking wires thinner than a human hair from the silicon die to the external pins. And then you have to encapsulate the whole thing in a protective resin.
That sounds incredibly delicate. And they have to manage the heat, I imagine, once it's encased like that.
Oh, thermodynamics are a massive part of OSAT. If the packaging doesn't dissipate heat properly, the chip literally melts the second you turn it on.
Wow.
Yeah, and after the assembly part is done, the test phase begins. You put these packaged chips through thermal cycling ovens, you blast them with electrical stress, you subject them to intense physical vibration to ensure they won't fail when they are put into, say, a car engine or a biomedical device.
So it's highly technical, it requires extreme precision, but it doesn't require a $20 billion clean room just to get started.
Exactly. It's accessible, but still highly valuable.
Yeah.
So the pragmatic roadmap here is basically threefold.
Yeah.
Step 1. Master the foundational design of ships and high-performance antennas locally. Step 2. Dominate the OSAT ecosystem, the physical packaging and the extreme testing.
That's third.
Step 3 is, as those tech eagles finally return from places like Colombia and Rice, they bring their global patent knowledge back and gradually evolve the nation into a regional R&D hub, a place where original inventions are born, not just a place that provides cheap outsourced labor.
It allows them to integrate their own technology into domestic solutions immediately. Like they can design the mining sensors for quinine and the medical devices in-house.
Precisely.
And the interview captures this whole philosophy in one piece of advice Dr. Nghiem gives to the youth. He tells them, don't choose the easy job, choose the valuable one.
Yeah.
He uses this metaphor of a tree. He says a tree with deep, hard-to-grow roots bears the most precious fruit.
It is such a brilliant way to frame a career. Because if a skill is easy to acquire, everyone is going to do it, and your market value drops to zero.
Right.
But if you take on the brutally complex physics of electromagnetic fields, or you master the frustrating microscopic thermal dynamics of OSAT packaging,
You build deep roots.
yes, you build deep roots, you become completely irreplaceable.
So while other nations might chase the immediate prestige and the big headlines of trying to build a massive foundry they just can't sustain, Vietnam can quietly build this army of elite, battle-tested technicians who control the vital physical arteries of modern technology.
It is a phenomenal journey to track. I mean, we started with theoretical sparrows who knew the textbooks but froze up in the lab.
We saw an elite academic prove that real mentorship requires getting mud on your boots, literally taking students into coal mines to demonstrate that science has to serve humanity in the darkest, most dangerous places.
We examined the strategy of leveraging full-ride scholarships to expose those students to the absolute peak of global R&D, trusting that they will return as tech eagles to build up their own nation.
And we explored a remarkably sober economic strategy, avoiding the multi-billion-dollar foundry trap and instead building an unstoppable tech sector by mastering the messy, complex reality of OSAT and antenna design.
It really is a masterclass in long-term systemic thinking.
Which brings us back to you listening to this deep dive right now. We live in a world that is, frankly, obsessed with the quick fix.
Oh, for sure.
We are bombarded with life hacks, AI shortcuts, and just the promise of the easiest path to the fastest possible result.
And Dr. Nghem's philosophy challenges that entire modern mindset, the tree with deep, hard-to-grow roots metaphor. It asks you to evaluate your own trajectory completely differently.
So as you go about the rest of your day, here's a thought to mull over. In your own career or in your own industry, what is your deep root skill? What is that one difficult, highly technical, or complex niche that everyone else is avoiding just because it's too messy, too frustrating, or takes too long to master? And how can you turn that exact difficulty into your ultimate, irreplaceable competitive advantage?
Because at the end of the day, the hardest problems to solve are almost always the only ones truly worth solving.
Beautifully said. Thank you for bringing these sources to the table and joining us for this exploration today. Until next time, keep digging deep.